Everyone. So let's start the first lecture on the introduction to quantum information and associated technologies. So my name is Christophe Couteau, and I just want to first to tell you about this series of lectures because they're a bit special. So the name code, you always need a name code. This QX01 is actually an experimentation because it's the first course, at least for the UTT, that will be with lectures live on YouTube. So this today is not exactly live. It will be recorded and later on YouTube. But for the following weeks, I believe it will be live on this website, this UTT channel, YouTube channel. So it will be every Tuesdays from 10 to 12 a.m., so Central European time. Although, as you will see in the planning, there will be some days where there will be no lectures. And so one reason why we wanted to do that out of an experimentation, as I said, is also for the topic itself, as you will see today. It's very trendy. So to speak, and there's a growing interest for it. So a few sort of practical aspects. There will be no live scientific moderator you can use. So there's a chat on the YouTube, so you can use it. But whatever you have scientific questions, they will be recorded and answered at a later time. There will only be a sort of a standard moderator, just in case, which means that you can leave your comments and questions on the website and they will be answered later on. Another last important point is that this is a University of Technology of Troyes lectures, meaning that some of aspects might not be relevant to everyone, but only to the students, and mostly to the students who actually follow this course. So perhaps I could start by introducing myself a bit more. So I'm a physicist, and that's important because, as you will see later on, that QX01 and quantum technologies actually encompassing just maths, computing, and physics. So I always have a physicist point of view. So I'm a professor at the UTT, and I work also at a laboratory called Light Nanomaterials and Nanotechnologies, which is a UTT CNRS research unit. And I'm actually the director of this research unit. In terms of what I do at UTT, so I teach, like today. So those are various courses that I teach, which do not speak to everyone, but basically I teach physics mostly, from classical mechanics up to quantum mechanics. Research-wise, when I'm not teaching, I do research. These are the topics I'm working on. So I'm on quantum optics mostly, but nanophotonics, semiconductor physics, and of course, quantum information and technologies. And a brief CV, again, to introduce myself. So I have a master's degree in physics from the University of Paris-Saclay. I also have a PhD from the University of Paris-Saclay and Grenoble University. And I have a research habilitation from Sorbonne University a few years ago. And I worked in various places around the world, mostly working on quantum technologies, in fact. I firstly worked at the Oxford University, but also at the University of Waterloo in Canada, and more recently at the Nanyang Technological University in Singapore as a visiting professor. And for UTT students, of course, if you want to know more about research, there are ways of interacting through projects, internships, or exchange semesters, and so on. So again, this is very much a slide on dedicated to UTT students. Here's the official description from the lectures book. And a few things that are not really there. So first of all, there is almost no prerequisite, in a sense that this course, and that's one of the, perhaps the biggest ambition of this course, is to be accessible to any student, third-year equivalent student, with some form of scientific background in physics, math, and computer science. Okay, this ideally all is required is a minimum background on these three topics. Okay, but it's not targeted for physicists, it's not targeted for computer scientists, and it is not targeted for mathematicians. In terms of, as I said, experimentation, so there are several novelties on this course. The first one, as I said, is that it's the first course open to all students, all engineering students of the UTT, which is for us a first, in a sense that usually scientific courses are more for applied mathematics or computer science or physics, but in here again, this one is supposedly for everyone, or accessible to everyone. It's also a UTT first in a sense that it's going to be live on YouTube, as I said, again, part of this experimentation. And it's also the first course on such a subject at the UTT, okay, purely dedicated to quantum technologies and quantum information. For the UTT students, not for the others, quick word on the assessment, although this might change. There are, say, 3 parts. So there will be 2 exams, so a midterm exam and a final exam. There will be some lab works, which I put in here. And there will be a project, which is most likely going to be to write a review article on a specific topic related to quantum technologies, and most likely there will be at least a group of 2 people, maybe 2 to 3 students. For the practical work or lab work, in French it's called travaux pratiques, we have these 4, which I'll come back to it later, where we're going first to look into classical gates for computing, and we're going to talk about quantum computers and quantum gates, but first you need to know, to have the basics of what are classical gates and how these wonderful wonders actually work. There will be also, there's a very nice way of getting introduced to quantum concepts that we'll talk about through a board game called Entanglement, which is an IBM, done by the company IBM. There will be another practical work on quantum gates and algorithm using, again, the online IBM simulator. And there will also be the equivalent using the Atos, the French company Atos simulator. And finally, there will be sort of more hands-on lab work, which is going to be an introduction to quantum key distribution and entanglement and Bell inequalities, where we're going to use photons, light, as a quantum bit of information. But I'll get back to that later on. And these might change accordingly to the needs during the semester. In terms of planning, so today is the first lecture. As I said, there will be lectures every Tuesday or so. I'll show you the more clear planning later on. Next week, starting the travaux dirigés in French, so the so-called tutorial work. They will start next week. Probably around mid-March, we will introduce the start of the project I was talking about. And then probably around beginning of April, we will start the lab work. There will be a midterm exam somewhere. There will be the project due back, most likely sort of mid-June. And there will be a final exam on the week of the 21st of June later on. So, here are the 14 lectures that we're going to address. So today is Introduction to Quantum Information and Technologies, which I'm about to start. And next week will be a lecture on, again, as I said earlier, on classical information in computation, in order to grasp the power of quantum information in general. Then you need to know what we compare it to. The week after that is holidays in France, or this is sacred, so there will be no lectures. And the third one will be on the 8th of March, and we will really start there as such, the subject by introducing the notion of qubit, quantum bit, the equivalent of the bit of information in the quantum realm. And then the other lectures, so far those three are confirmed in that order. The others are all confirmed, but two things that is not confirmed is perhaps the order might change as we go along. And also, as you can see, 4 of these lectures will be given by outside colleagues, 3 from companies. So the British company called QX, which works on quantum cryptography and related topics. The French company Thales on quantum sensors. And the French company Atos, which I mentioned already, will introduce the simulator, the quantum simulator that they have. And then there will be, so it's not a company, it's the INRIA, which is basically the Computer Science National Institute of France. And there will be a colleague there talking about algorithm, so perhaps not Shor's algorithm due to strain, but another time constraint, but perhaps another algorithm at the time. And then you see all the other topics that we will talk about, so multiple qubits and the notion of entanglement, very important. The notion of measurements and operators, which is more of a quantum mechanics, quantum physics notion, but we'll come back to that. Quantum cryptography, quantum gates, quantum algorithm, quantum sensors. So you will see that these topics seems to be unrelated, but they are, and I'll tell you how later on. Quantum error correction as well, very important. And probably near the end, we will talk a bit more about physics by introducing some different technologies. Because mostly, in order to apprehend all of these topics, in terms of physical means, what we will use is mostly the notion of qubits using single photons and the polarization of light as a way of encoding quantum information. But there are other ways of doing it. There are other type of technologies, like superconducting technologies, or trapped atomic ions, and so on and so forth. So those most likely will be discussed in a bit more detail at this stage. Right, so what are we going to talk about today? So today is, as I said, is an introduction to quantum information and technologies. So we could call it QIT. And there will be 5 topics. So the first one, perhaps the most important, is why should we care? Why should you care? The second one is, how is it so different? And you will see that it is very different. The third topic I will address is, of course, as any course, you need to introduce a bit of history. Where are we coming from? Okay, so a very brief history of quantum information and technologies, but it is interesting. And the fourth topic will be, well, what about the market? Because these are not lectures on quantum physics, these are lectures on quantum technologies, all right? So quantum technologies means innovation, means products, selling things, using things. So is there such a market for that? So this is a valid question. And then I'll finish by introducing in one slide some keywords and concepts that hopefully at the end that will not be clear to you today at all, but hopefully by the end of these 14 lectures, will be some of the questions and some of these concepts will be answered. So, why should we care? So here is an example of an ICT wall, so information, technology, and communication. And as you know, ICT, so information, technology, and communication, is basically pretty much everything these days, especially in the last year or so. But it was, and it is, and it will be anyway. So why is that? Because information is basically everything, from multimedia, to software, to business, to mobility, telecommunication, e-commerce, etc., etc., etc. And this is just the beginning of it. So this is a fact, and we are living with it as we speak. In fact, this is a very good example of that. But why then should we care about introducing quantum information and technology? Why is it so important? Well, because you will see that for ICT, so the classical equivalent of information and technology and communication that we are using these days, there are mainly two limitations to how far we can go with these classical technologies. And those are very important limitations because they are given by nature, which means that we cannot beat them. All right? So we know already that we will be facing these limitations. In fact, we already are facing them. So, so the first one, as you probably heard from before, is the so-called end of Moore's law. So this man, Gordon Moore, is one of the co-founders of Intel. He was CEO and co-founder of Intel. And so there's a famous prediction by Moore who says that, as out of an observation, is that in electronics, computing, and all sorts of electronic devices, the number of transistors in an integrated circuit, like this one, doubles every 2 years or so. All right? And as you see here, so here it's not that clear, but here is a semi-log plot of the number of transistors, so in semi-log plot, so in log scale and for the y-axis, as a function of time. And if you can't really see, so here's about the time that I was born, so 1970s, up to 2020. And you can see that the trend is pretty much valid. So Moore was right, and that's why we've been talking about this law for decades now. But there is also, up to here, and that's going to so nowadays, and that's going to increase, there is, though, a limitation to that. Okay? So in other words, the reason why we can do that, what Moore's law was, is still true somehow, is because we've been able to reduce the size of transistors every few months or every 2 years or so. We've been able to reduce them technologically. But this reduction in size has its limit. Okay? So if I take, if I take, for instance, this graph, you will see that size matters. All right? And that these days we are at about 5 nanometers technology. And this is a graph by the Taiwan Semiconductor Manufacturing Company, so TSMC. And again, what do we have here? We have the size of the transistors, typical size, as a function of time. All right? And here, so the plot starts at 1987 up to 2019, where we are pretty much, so it's about the same thing as what we are right now. And indeed, the size has been decreasing from 3 microns to 5 nanometers. So I'm not going to go into the details of, I'll mention that a bit more the next lecture, but I'm not going to go into the details of what do we mean by these typical sizes. But roughly, at this stage, what you need to know is that in a transistor, at some point, there is a thin layer of oxide, which we call the gate oxide layer, which is an insulating layer where electrons, current electricity is not supposed to go through. And this is the modulation in a transistor that allows the flow of electrons thanks to this oxide layer. And this is typically, let's say this is going to be our typical dimension for that. So these days we are at very small scale. So typically these layers are on the order, as I said, around 5 nanometers, 7 nanometers. And just to recall, I'll remind you that nanometer is 10 to the minus 9. So 1 nanometer is about 10 to the minus 9 meters. And to give you an idea, roughly the diameter of one of your hair depends on where you're from. Europeans have thinner hairs than some others, for instance, but roughly the typical size is around 20 to 50 micrometers, okay? So to give you an idea, so diameter of your hair is around 50 micrometers. So 50, 10 to the minus 6. So you can see roughly the orders of magnitude that we're talking about, to 1,000 to 10,000. Right? Yeah, one quick word, because when you put things on YouTube, you never know where it goes. This is the French way of writing ones. So this is not a 7. So please excuse us for that in advance, but these are ones, okay? So, okay, so you could say, what's the big deal? What's the problem with that? It's small, and so what? If we can make it technologically, which we can, then what's the problem with it? Well, the problem is that typically at this dimension, and I'll come back to that later, is that we have an effect that we call quantum tunneling, all right? And quantum tunneling, in this case, is a big issue. So why is it a big issue? Because, so as I said, typically in these transistors, so again, I will come back to that, but just to give you an idea, in these transistors, there is, at some point, an insulating layer. So insulating means that current is not supposed to flow through it, right? So when this layer is thick enough, then there's no problem. The electrons do not go through. But when this layer is thin enough, which is typically the orders of what we're talking about here, 5 nanometers, then we say in quantum physics, in quantum mechanics, that the probability for an electron to go through this layer now is not 0 anymore. Right? So in other words, it means that this electron can actually tunnel through this barrier, this wall, that is not supposed to. Okay? And that's a problem, because, well, you're supposed to have an insulating layer, not a conducting layer. Okay? And you could say, okay, well, maybe it's a question of material, maybe it's a... Well, actually, no. It's, again, it's the very fact of nature, of quantum physics, that tells you that this effect does happen, no matter what you do, when you are at these type of dimensions. In fact, like I like to say, quantum physics, just to be clear, and again, we'll come back to that in the notion of superposition, but quantum physics is a theory that tells you that if I run against that wall, there is a non-zero probability that I will go through. Okay? So of course, this probability is infinitely small. So most likely, I will hurt myself. So it doesn't work at our scale because we are big objects. But it does work at this scale. So typically, this electron going through this wall of material will go through, will tunnel through. Okay? And is at some point in a superposition of being on the other side of the wall and on this side of the wall. Okay? Again, as opposed to us, which will only be in one side of the wall. But there is a probability. It's very, very, very small, but it's not zero. That's what quantum physics tells you. And that's the main property we're going to use for quantum technologies. The second limitation is the fact that some problems are actually unsolvable. So for instance, there is an optimization, for some optimization problems, there is the so-called traveling salesman problem. And so here's the problem, is you have a salesman who sells, I don't know, quantum computers maybe. And he's got a list of cities he has to go through. And he's got the distance between each pair of the cities. Okay? And the question is, what is for him? I mean, of course, this man wants to sell things, okay? So his time is very precious. So his problem is to say, well, what is the shortest possible route that I can take to visit each city exactly once, okay, not more, I don't need to go twice, and return to the original city in the shortest time. So this is what we call an NP-hard problem in combinatorial optimization. An NP-hard problem tells you that this is a problem that takes an awful long time to resolve. So this was supposed to be an animation, but you can find it on Wikipedia. There is the same animation, for instance, and you can find it on the web, where you can see in real time. So here, these dots are supposed to be the points that the salesman is supposed to go through. And then there is a calculation that takes some time. It's live, and you can see it's very well done. And it gives you what is the shortest time in order to visit all the cities once. And you can see, even with this example, where there are only 7 points, that it is by no means a trivial point. It takes a long time. It takes a lot of calculations. But this is just one example, but there are actually, especially in optimization problems, but not just, there are many other problems that we don't really know how to solve in a short time. There's another computing problem, which is the so-called halting problem. So what is a halting problem? Is you have you have a computer, you insert an input string, and you run an algorithm, and you want to know when you're supposed to stop the algorithm, when the problem is solved. That seems sort of an easy thing to do, but is actually not at all. So that's more on sort of computation science problems, but there are also problems in physics that are very difficult to solve. Right now, for instance, so in physics, usually what is important is in order to know a system, so I will get back to that concept later on, but you need to find what we call its wave function. The wave function defines a system, an atom, an electron, you, me, a table. And what you need to know is what are, in order to know quantum mechanically this system, you need to know what are the different energy levels of this system. And as of today, we know how to do what the hydrogen atom, which is the simplest atom you can think of, and the hydrogen atom is simply one proton and one electron sort of gravitating around it with a Coulomb force in between, interaction between a plus charge and minus charge. So quantum mechanically, we can solve that problem perfectly. In fact, it's an analytical problem. Not trivial, but we can do it. But then as soon as you start to go from helium atom, which is not that much more difficult, not much more complicated atom, because helium atom is the next one in line, it's 2 protons and 2 electrons. So that already is a 4-body problem, and that already is the limit of calculations of non-analytical calculations that we can do, pretty much. Okay? So needless to say that if you want to go further for more complex molecules, like this nasty one, for instance, then there is no way you can define perfectly today with a computer all the properties of these molecules, all the energy levels, the entire wave function, the entire system itself, which you can perfectly for hydrogen, but you can't for that. Of course, we still can work, luckily. We can make vaccines, for instance, and that's because we have approximations. So, of course, we are not stuck to hydrogen. We can go further by approximation. But it is limited, this approximation, then there are approximations. So it would be nice if you could still compute perfectly any molecules, or at least some important molecules, like disease, viruses, and so on, or other things. But for the moment, it's not possible. In fact, for some of these problems, it is possible, but it would take around the age of the universe with our standard computers. So that's not very reasonable. And in fact, for some of these problems, optimization or physics or other problems, and there are many other problems like that that seem unsolvable, in fact, we already know, because you could say, well, you just need to wait, because our computers are not good enough now, but maybe in 10 years, 20 years, 50 years, they will be good enough. Well, actually, no. We already know that classical computing, as we use it, will never catch up for some of these problems. So they will never be able to solve some of these problems, or at least not within a reasonable time. Okay? So these are the 2 main limitations for what I would call classical information and computing power nowadays. Okay? So we need something else. We need a complete change of paradigm. Okay? And for that, the idea is to say, well, how about we could make use of quantum physics? We already make use of quantum physics in everyday life. Transistors, lasers, everything is already using quantum physics. But it's using quantum physics, but not as at its core. Okay? Not at its core in a sense that, as we will see later on, that quantum technology is about using what defines quantum mechanics, okay? And we will see what defines quantum physics, quantum mechanics, which is mostly the notion of, as I said already, of superposition, of quantum tunneling, also entanglement that we will discuss later on. Okay? So again, back to the question, so why should we care? Why should you care? Well, because when I was a student 20 years ago, it wasn't clear whether quantum, at the time it was called quantum information, would become a technology. Nowadays, as you will see later, it's pretty clear that before the end of your lifetime, you will have to encounter quantum technology somehow. Okay? And also because it is pretty clear now that nowadays we can control quantum physics enough for some of these applications that we will see. It's already the case. And it's also interesting because there are some major engineering issues and challenges. So that's why you should care. And, the comparison to how we are now with quantum technologies to how we were 60, 70 years ago, when the first transistors were coming out to build computers as we know them now, there's a parallel between these two. Okay, it was the same 60, 70 years ago when the first transistor came in. They say, yeah, okay, it's interesting. We can make computers, and so what? Where is this going to lead? Well, you can see where is this going to lead. So, hopefully we can hope that quantum physics making use of quantum physics will do the same in, I don't know, many years' time. And another aspect that only the oldies like me in the field remember, and that seems to be the trend now, is that this is one of the great examples I find that is fully multidisciplinary. So back in 2001, I attended a winter school in Les Ouches. So it's a famous site for scientific schools. It's in the Alps. It's a small village, and it's a retreat, basically, and you go there, and so I was a master's student at the time, and I follow courses on quantum information. Like I said, at the time it wasn't called quantum technologies, it was called quantum information. So apart from the fact that food was great and that the view was nice, because you could see the Mont Blanc from basically your window, what struck me at the time is, as I said, for perhaps the first time, quantum information would gather different communities: mathematicians, computer scientists, and physicists. And in fact, even for physicists, which I am, it was quite of a shock, because usually in physics, we don't mix so much. It is so, when you work in a field, you can't really be doing everything, okay? So something that we'll never do in my lifetime, most likely, is astrophysics or nuclear physics, but also maybe superconducting physics. So, which means that usually in physics, at least, when we go to a conference, we meet people that are in the same area. So in my case, sort of optics, nano, quantum with nano in optics, but not necessarily the others. If you work on superconducting materials, then you don't go to the same conferences. If you work on semiconductors, you go to another one. If you work on anything else that is not directly related, then you usually do not meet. Atomic physics, for instance. But in here, so in this school, there were people from all over disciplines. There were people working on, like I will mention later on, trapping single ions in an electric trap. There were people doing some high-end electronics with superconducting physics for superconducting qubits. There were people using photons, people using semiconductors, and so on and so forth. And there were computer scientists and mathematicians. And all of these people had something in common. The first slide usually is, okay, what is your qubit? Qubit, I know what it is, so at least I can start here. So you work on quantum technology, so you have qubit entanglement. Okay, so that I understand. And now in your technology, then you use superconducting or mass or some algorithm, but that's sort of a second layer. Okay? So this is something that we take for granted these days, but it wasn't trivial at all at the time, and at least for that reason, the subject is very interesting, or at least I find that. So, again, why should we care? Well, you may have read or seen or heard that there is now what we could call a quantum effort worldwide. Okay, there is a growing interest. That is a fact. Okay, so here it's a map of the world where we have an estimated effort in quantum technologies that is roughly around $20 billion worldwide. So in Canada, in the US, in Europe, India, China, and so on, Australia. And in Europe, you have the European Union, for instance, that came up in 2009, what we call the EU quantum flagship, but also some single country related program, like recently the French president announced the Plan Quantique, so the quantum plan for France, so that was a month ago. You had the equivalent in the US with the US National Quantum Initiative Act in 2018. You have also an equivalent in China, and so on and so forth. Okay? Even sort of smaller countries like Israel or Singapore have their own quantum effort program. So that's why you should care, because if all these people think that they should care, then perhaps we should care as well. So the next question is, as I said, is why quantum technology is so different. Well, here are some keywords I'm giving you today that hopefully we will be able to grasp more as we go along. But I gave you here, in essence, why it's very different is because, as I said, what we want to do is to actually use the law of quantum physics for applications. So laws of quantum physics, so the rules, so to speak, it's like a game. There are always some rules. So the rules in quantum physics. The first rule is you have what we call, I mentioned it already, the notion of superposition, of quantum superposition. And perhaps you heard, you know of the famous Schrodinger's cat problem, where it's redefining the same problem as I said earlier when I said, I run against that wall and there's a probability I can go through. Well, so Erwin Schrödinger had equivalent with his cat. Is he said, well, assume that I've got my cat in a box completely sealed, and assume that inside that box there is a mechanism where you've got a hammer that can break a bottle. And in this bottle, there is some poison, some poisonous gas, meaning that as soon as if the hammer would break this bottle, then the gas would go into the box and the cat would die. Right? So that's pretty clear. But now you can see that this hammer is linked to a handle. Okay, so meaning that the handle. So if you press the handle, you pull the hammer and you break the bottle. And this handle here is or not activated by the radioactive decay of an atom. Okay. Because one of the things that you learn in quantum, when you learn quantum physics is the notion of decay, of radioactive decay. What it means is that some atoms can radioactively decay with a certain probability. It could be 50% probability to decay at a certain time. So it means that this handle here will be activated if the atom has decayed, but will not be activated if the atom has not decayed. Okay? But as quantum physics that tells you that you can be in a superposition of both, that this radioactive decay happens with certain probability 50%, or not happens with the probability of 50%, then that means that somehow, whether the hammer will break the bottle is somehow in a superposition, like I was earlier, or if I run against that wall, or more to the point, this electron tunneling through this layer. This hammer is in a superposition of breaking the glass and not breaking the glass, meaning that the gas, the poison gas, has a probability 50% of being released and 50% of not being released, meaning that the cat itself is well, in a superposition state of being dead and alive with 50% probability each at the same time. So we will see later on how we write that, how we define this mathematically. It looks like this, where you have this weird sign, which is the wave function of the system. So this would be the wave function of the cat. So what describes the cat. And you can see that what describes the cat, in this case, there is a plus here, meaning that the cat is in two states, is either alive or dead. So that was Schrodinger's cat problem. They say, well, if quantum mechanics is true, for electrons going through, or not, a barrier, a material, that means by extension I can extend it to anything, and maybe to my cat in that particular case. Of course, it's not that simple. There are many reasons why this will not work. For the same reason as me earlier, because if I go through that wall, I will hurt myself. So this probability of being in a superposition state of dead or alive for the cat is actually very, very small. So it doesn't work. But again, this works for electrons, photons, and so on. So it does work, and we can use that. The second sort of non-trivial aspect, but very important for quantum technologies, is the fact that there is a so-called no-cloning theorem. So quantum physics is actually very simple. At some point, I will demonstrate that to use a very simple demonstration. But what the demonstration tells you is that if I have a quantum system, so with this wave function, again, so I will use that term. When I say wave function, again, is what defines the system, so it's the entire system. I've got a wave function, so do you. But in this case, it's more the electron or the photon. So this system, this wave function, if you want to put it in a box, in a machine, that can clone it, so make an exact clone of this wave function, so 2 copies, quantum physics tell you that this is impossible. This is not possible, okay? You can get close to that, but you cannot get a perfect copy of your input state, of your input wave function system, okay? So a perfect clone does not exist in life, in nature. Physics does not allow it. So you'd say, okay, so what? Well, this is great, as we will see later on, because we can use this particular property for, say, quantum cryptography, for instance, because that tells you that if you use quantum physics for cryptography, then you cannot make copies in the quantum world. Already you can see that the interest of that for communication is important. The third notion that is also extremely important is the notion of quantum entanglement. Okay? So in French we say intrication, or for the old people like me, we say enchevêtrement. But nowadays people say more intrication. In all cases, so entanglement or intrication, whatever this actually derives from the German term that I will not dare to pronounce here. But at least in English, there's only one term, which is the notion of entanglement. So what is entanglement? Well, entanglement tells you that if I have 2 coins, so these are 2 coins, so one with 2 sides, heads or tails. In this case, one of them is 1, and the other side is 0. Same for this one. So entanglement tells you that if these 2 coins would be entangled, the probability would be the following, is that if I give you one, and if I keep the other one, no matter what is the distance between you and me, if these 2 systems are entangled to start with, that means that there is a higher correlation between the properties of these 2 systems. And how do we find this correlation? How do we evidence this? Well, it's very simple. Is that when you have your coin, you will make a measurement. So say you measure your coin, you look at what your coin gives you. Say 1. Okay? Well, entanglement tells you that without talking to each other, if I do the same with mine, then I will find the exact opposite, or by the exact complementarity, and I will find 0. And so this is for one instance, and we can do it again and again and again. And if these two systems are entangled, so if every time I am able to produce new systems of entangled coins in this case, and share them between you and me, then I will always have this property. Meaning that no matter what you will find, whether it's 1 or 0, I will always find the counterpart, so 0 and 1. Okay? No matter what is in between us. That's you, before you do the measurements, before you look at what you're going to find, you don't know what you're going to find, of course. It's heads or tails, you don't know that until you look at it and find, say, 1. So it means that intrinsically, on your side, you don't know how much you're going to find. You're going to find a probability of 50% between 0 and 50% of finding 1. That is purely random. You do not know what you're going to find in advance. But what you do know is that once you found the result, is that when I'm going to make my measurement on my side, then I will find the exact opposite. I will find the exact correlated result every time. Okay? And this is the power of entanglement, and this is at the heart of quantum computation and other applications. Okay? We'll come back to that in a bit more details, and we will see how also we can actually do that physically with the physical system using photons in this case. But there are other properties, like for instance another one that again on paper is plausible, is quantum teleportation. So quantum physics tells you, if you're a big fan of Star Trek, that you can do teleportation. You can ask Scotty to teleport you to wherever you want. Quantum physics says it's been proven that quantum teleportation is possible. Of course, again, it's the same thing as earlier, if I want to teleport you, or even something remotely small, then it will be very, very complicated. Okay? You will have to use quantum entanglement, but I'm not going to go into the details of that, but it's going to be very, very difficult. So in practice, for you, me, it doesn't work. But for, again, particles or small systems that are quantum mechanically controlled, then you can do teleportation. In fact, it has been done with the polarization state of photons in the past, and it's still used nowadays. So you can do that. And so using all these properties, one thing that comes out of it is the notion of quantum parallelism. Okay? And that, so for now, is a bit unclear, but later on, I hope by the end of the semester, it will be clear that what we mean by quantum parallelism and why this is so much different than the rest, than the classical equivalent of doing, information and dealing with information. And we will see that there are potential applications in artificial intelligence, optimization problems, I mentioned that already, computation in general, but also other properties and other technologies in sensing, quantum sensing. We will talk about this later on, and communications. And I gave you the importance of the no-cloning theorem for quantum communications, quantum cryptography. So again, I come back to, how is it so different? Well, it is so different because, as I mentioned it already, you need to be able to deal with these three aspects at once, with math, with physics, and with computer science. Or at least you need that today. Perhaps, in 20, 50 years' time, when you will be a quantum computer scientist, then you don't actually care about what the physics is below. Like nowadays, when you code on your computer, you actually don't really care and don't really know how your computer works, because you don't really need that. You do computing science. But as of today, you need these three aspects. And you need engineering now to be able to bring these three aspects together. Okay? So here I reproduced a sort of roadmap, or say sort of vision view of the quantum flagship. I mentioned it, the European Union quantum flagship, it's a quantum program from the European Union. And it has been identified that in quantum technologies, I already mentioned it, but just to make sure we put it down, there are basically four main applications that have been so far identified. So the first one is in computing, quantum computing. The second one is, we will see that later on, is quantum simulations. So there is a difference between computing and simulation, in a sense that in quantum technologies, when we talk about quantum computing, we actually mean to build a real standard universal quantum computer, which as of today we cannot do. Okay? So people talk about quantum simulations, where maybe we can still use quantum simulation to solve some problems. There's quantum communications. I already talked about it. And also, as I said, quantum sensing and quantum metrology for metrology aspects is also can also be useful. And of course, the European Union, so this is pretty much shared by everyone, by all countries. In the US, they would have something similar as well. So you have these four pillars, and you have sort of transverse ways of dealing with it. The first one is, of course, you need engineering control of all of this. You need education and training, and this is why we are here today. And also, you need a lot of software and theory, not just practical work. As we will see, there is still a lot to be done. And all of that, of course, as I mentioned, as of today, you still need a lot of basic science. Okay? So even though you have an engineering part that can give you a job tomorrow in a quantum company, you can also do a lot of basic science, because we still need that as of today. So for that, as I said, there will be, in this class, there will be four external colleagues coming to sort of illustrate each of these pillars. So the company KETS on quantum cryptography, Thales on quantum sensors, Atos on quantum computation, and the INRIA, so the National Computing Institute, French Institute, for the simulation aspect and also computing aspects. One thing I do not know as of today, that's why I said it's tentative planning, is I don't know. We still have to discuss if these lectures will be available on YouTube. That I do not know, but you will know later on. One thing also I thought I should do is, because these lectures are supposed to be aimed for math, physics, and computer science, Then I will try to sort of put a small logo on the right-hand corner to illustrate at a given point what field I'm going to address mostly. So whether it's physics, whether it's math, or whether it's computing. So in some cases, there will be 3 of them. In some cases, there will be just a pair of them. In some cases, there will be just a single one. But again, it's to illustrate, and at the end, I do not know that. At the end, what I will do is I will count how many times I put each of them, and we'll see if there is an equiprobability of using these logos of math, engineering, and physics, computing and physics, and see if indeed these lectures did do what it's supposed to be, as in address each of these aspects. So now I'm going to give you a brief history of quantum information and technology, QIT. So again, of course, as I said, I'm a physicist, so there is some bias into it, in a sense that for this particular case, the brief history will encounter mostly physicists, but in a way it's fair enough, because computer science and computing math and so on did do his own dig on the side, and quantum physics did his own on its side as well. So it's only recently, as you will see, fairly recently, that these worlds started to mingle, started to meet each other. So physics-wise, where are we coming from? Well, in terms of quantum information technology, between, say, 1900 and 1980s, we are in the sort of prehistory of QIT, okay? And why is this? Because it's more the history of quantum physics and quantum mechanics, all right? And here I give you some examples of important people, but the main ones, but there are many others, okay? Maybe the most famous ones for particular reasons, but of course this is a non-exhaustive list. But in this prehistory of quantum physics, what we have few important aspects, like the notion of quantization and the famous Planck constant h, or h bar, which is simply just to make sure. So h is called the Planck constant. And usually we like to use h bar, which is simply h divided by 2 pi. H divided by 2 pi. And we like to use h bar because we have 2 pi a lot everywhere. But it doesn't matter. What is important is the notion of quantization that came with this very important constant that Planck had to introduce in order to understand some of the physical observations at the time, so around 1900s, and like the so-called black body radiation, for instance. And then there were other aspects that were sort of studied and thought of at the time, like the photoelectric effect by Einstein, and also the first sort of theory on what an actual atom looked like by Niels Bohr, where Bohr said, well, actually, in an atom, what we have a nucleus and we have electrons around it, but these electrons, as opposed to what we thought before, so it's the so-called planetary model, can only have discrete energy levels. Okay, they cannot have any energy level. So quantization in that respect tells you that the energy associated to a particle, in this case an electron inside an atom, cannot be continuous, it's quantized. Okay? And then there were some very important notions, like the notion of wave function. So this sort of, psi, with this weird notation that we will get back to it. So for now, just take it as a notation. It's the so-called bracket notation, but we'll come back to that later. And then the notion of superposition, as I mentioned before, like Schrodinger's cat. And then some oddities, like the so-called Heisenberg uncertainty, that you may have heard of it, where the Heisenberg uncertainty tells you, again, which is another way of reformulating quantum mechanics, that an object that you cannot measure the position and the speed, or the speed of an object with the same precision, that you either have to choose, so either you are very accurate in position, but less so in momentum, so in velocity, or you are more sort of precise in measuring the velocity of the particle, but then you lose some information into the positioning of the particle. Then there is also, so Erwin Schrödinger, oh, there is a bit of a mistake here, it should be Erwin Schrödinger, which came with his famous Schrödinger equation, not just a cat, which basically gives you how, at least in physics, a system should behave, okay? So how this wave function can behave in time. So I will come back to this equation later on, although not too much, because for what we do, it's important, but it's already a bit too much of physics, perhaps. So we will use it, but with parsimony. So that was sort of the prehistory of QIT. And then we have a jump, because between, say, the 1920s up to 1980s, people were busy sort of understanding physics and application using quantum mechanics, but not using the sort of intrinsic properties of quantum mechanics, as I said, like entanglement, superposition, and so on. So first connections, again, this is a selective view, but it's not the whole game. Of course, it's much more complicated than that, but maybe there are some important dates. So the first one perhaps was in 1980, which was the first conference on the physics of computation, which of course was held at the MIT. And there were people, a lot of bright people, and two of them came with some ideas. So the first one was Paul Benioff, and the second one with the sort of the famous physicist Richard Feynman. And these two, as well as some others, started to question the physics of computation. And of course, if you start to question physics, then usually it always comes down to, what about quantum mechanics? How does it come into play? And during this conference, and around that time, there was some question on whether a computer can actually operate under quantum mechanics rules, which was not the case at the time, and still not the case at the time, not the case these days. And one idea was to say, and that was by Feynman's idea, was to say, well, as I said earlier, remember I told you that to actually find out the energy level of an atom, so to actually simulate a real quantum system is actually very, very difficult. But Feynman postulated that, well, it is difficult to solve energy levels of a quantum system, for instance, the energy levels of an atom, but that's because you use a classical computer. But if you were to have a quantum computer having quantum rules, then perhaps you could operate and simulate a quantum system and use that quantum computer for that. And perhaps the notion of the so-called quantum mechanical Turing machine was sort of born at the time. Okay, sort of a universal computer using quantum physics could actually exist. So that was the first aspect. Another aspect that was sort of very important and still is these days in terms of application, because it's probably the far more advanced application, was in 1984 by these two gentlemen, so Charles Bennett and Gilles Brassard, where they came up with the so-called BB84 protocol, BB for Bennett and Brassard, and 84 for 1984. And this protocol was about how we can generate cryptography keys using quantum mechanics, and the notion of conjugate coding that was known in sort of standard classical physics, classical computation. So here was the first identification of a sort of real application that we could do. You know, the quantum mechanical Turing machine was more a bit of a dream really at the time, but this started the whole sort of quantum information idea of, hey, actually we could actually make something useful, you know. And then a year later, there was so David Deutsch in 1985 came with the first ideas and the first demonstration of you know, that an actual universal quantum computer using different rules with quantum physics with quantum bits could actually be done and could be the equivalent of what we have in the classical world as a universal Turing machine. So you could have quantum mechanical Turing machine. So we demonstrated that. Then here I put another date, another sort of quantum cryptography protocol. And why I put this one, this is the so-called Echot Protocol, or E91 protocol, because this protocol so again, it's the idea of conjugate coding for cryptography keys, but this case using quantum entanglement-based communication. And this entanglement I mentioned earlier, where in fact what it says is that, you know, we share some information that is perfectly correlated, and only you and I have the exact key correlation between these two coins in this case. So of course it is not going to work with coins, but it's going to work with photons, for instance. Okay, so with photons you can create a pure quantum entanglement state, and you can use that for quantum computation. And then perhaps what is seen as perhaps the major breakthrough came in 1994, where Peter Shor came up with his algorithm. And so what is Shor's, so is known as the Shor's algorithm. So why is it important? It's important for three reasons. The first reason is because this was the first, again, practical algorithm, as opposed to what was done before by other people, where you can see a true application, and more to the point, you can see a true power of having a quantum computer to solve some problems. And so what was the problem? So as you may know, in quantum cryptography, in classical cryptography these days, so is used in e-commerce, for instance. We use the so-called RSA factoring crypto system. So RSA are these three people who came up with it. So what is, in 2 words, what it is about? The idea is that if I give you prime numbers, then it's fairly easy for you to compute them and multiply them and make a bigger number, right? But the factoring is a much more complicated problem. So now if I give you a big number, huge number, and I ask you, give me the prime factors of this number. And this is one of these extremely difficult problems to tackle with a computer. You can do it, so computers can do it, but it takes an awful long time, and especially as the number of strings or the string numbers increases. Okay? But Shor's algorithm, using quantum physics, using these quantum laws, showed that you can have a gain. So you can go from, so it's not exactly that, it's a bit more complicated than that, but let's say it's roughly around an exponential n problem when you have n bits. Okay, when your string of numbers is n, then in order to find the prime factors, it's an exponentially n problem to solve. But Shor's algorithm showed that you could do that in a logarithmic way. And I will show you a graph later, because this is a significant gain in time. Okay? And it means that for a problem that was almost unsolvable, now we can solve it with a log scale in time, which is not very long. In fact, it's much better than a linear time. So that was my third point, is that this also brings up a question, because what Peter Shor showed at the time is that if, at the time or now, if I give you a quantum computer, then this could be a serious issue, right? Because with this quantum computer, you can pretty much instantly break any cryptographic keys that is available on the internet, on anywhere. And I don't think anyone wants that. So that's, it showed two things. It shows that it's very powerful, but it also shows that it can lead to some issues that perhaps will come back later, quantum communication could answer. But there was a significant step at the time to show the interest of quantum technologies, or again, quantum information at the time. And then came, so all of this was more sort of mathematical and quantum, computing science issues. And then, of course, came the first sort of ideas on how do we do that experimentally, because this is all very well on a piece of paper, but how am I going to implement that in real life? And again, there are many ideas, but perhaps one of so a key year was in 1995, where the first experimental proposal came in. So some of them using photons by these two gentlemen and others, or some of them using trapped ions by these two gentlemen. So what are trapped ions? They are basically ions, atomic ions, that you can trap using laser beams and electric electrodes. And you can basically have a string of them inside and control them individually or collectively. And why do I say that? Is because collectively means that these two gentlemen showed that using this particular system, which is what you would call an atomic physics system, you could realize what we call a C-NOT gate. So we will come back to that, but a C-NOT gate, or a control NOT gate, is perhaps the most important gate, or one of the most important gates that you can have for quantum information and for quantum computer. So that's the first sort of proposal at the time, where they showed how practically we can make this gate, this C-NOT gate, which is far from trivial to do experimentally, as we will see later on. And then in 1996, we should also mention another algorithm that was done by Love Grover, which is a search algorithm. So a search algorithm is a very simple algorithm. I mean, at least the classical one is, not this one. The search algorithm is simply, well, you've got a list of names, and I would like you to find whether my friend is on the list. Okay? So what a classical computer would do is it will go through the list one by one, and see whether the name of your friend is on the list. That's standard search algorithm. And typically the time it would take you to find that name is about the length of the list. So if there are n people on this list, it will take you sort of n proportional to n times to find it. But Grover came with an algorithm, which is in this case very useful, I mean perhaps even more useful than Shor's algorithm, where this search algorithm can be faster than n, but can find out if your friend is on the list or not with a time that would go with square root of n. Okay. Again, I will show you a graph later where you can see how much of a difference that makes. And then sort of the field exploded, and there were some first demonstration of Shor's algorithm, for instance, that was done in a lab using NMR, so nuclear magnetic resonance experiment, that was done by a joint work by Stanford University and IBM in 2001. And the first demonstration of Shor's algorithm, and just to let you know, was how we can find the prime numbers of 15. Okay, but still, it was quite an experimental feat at the time, and not trivial, and it showed that one can do it experimentally. And then some other proposals, some other experiments came. Perhaps I will cite one because it's also a famous one, is important for what we want to do in these lectures. It's the so-called Neal, Laflamme, and Milburn optical quantum computer that was also done in 2001 by these three gentlemen. And so it was a theoretical proposal, and it was important because it showed at the time that you could use, so I talked about trapped ions, I talked about nuclear magnetic resonance, we will see we have superconducting qubits, we have spin qubits, we have all sorts of different systems, physical systems we can use, but we can also use light, photons, and that's what we're going to use during these lectures to physically illustrate how we can implement that. And in 2001, so these three people showed that you can build a quantum computer with photons, which at the time was thought to be impossible. In fact, these three, I know that because I worked with one of them, and he was saying that originally, when these three started to work together on this article, what they wanted to prove is that you cannot build a quantum computer with single photons, with light. And the conclusion was at the end that, in fact, yes, you can. Okay, so that was their conclusion. And so on and so forth. Like I said, it's a very brief history, because especially the amount of work, proposal, experimental work, companies, as you will see, is just growing and growing in an exponential way. And since 2001 or even 1980, you can look at the curve of sort of article published in the field, and it's just an exponential growth. Okay. Alors, I mentioned this graph earlier. So this is a graph that gives you the so-called efficiency of an algorithm. So what you have here is you have here the number of input strings. So for instance, I mentioned this list earlier, so it could be a list of n people, so that's capital N. And as you increase this capital N, you have n, which is, so the number n is basically related to the computation time, to solve that problem. Okay? So this could be seen as the number of operations, and this could be seen as the sort of the actual size that you need to solve your problem. Again, which we'll say is sort of proportional to time. So in other words, that means that if you want to compute, say, a problem with a list of 10 people, so n equals 10 operation, then you need, so if with a classical computer, you need n sort of input string to solve that problem. And that's what I was saying earlier. If you want to find your name, your friend, you have to go through the list one by one until you're done with the list. So this behavior is a linear behavior. Okay? But then you can see that you have two families. So the ones that you don't really want, which are the ones that are exponentially hard to compute, which are all these problems I talked about earlier. So you can see here that the number of strings that you need to solve problems that are n log n or n squared or 2 to the n or n factorial just goes up to the roof in terms of operations. Okay? It's an exponentially difficult problem to solve. And then you have all these problems that you can solve in a much less time, and that's where you want to be. And that's where, for instance, Grover's algorithm or Shor's algorithm do lie. Okay? And you can see the difference between the square root of n solution problem solving compared to n or compared to n squared or 2 to the power of n. There is no game, there is no match here. Okay? So you can see here it gives you a clear view in one graph of why you would like to have a quantum computer for a lot of these problems that you cannot solve with classical computers. And then to finish this brief history, so perhaps I should mention, because I already talked about the fact that in 2001, these teams from IBM and Stanford, they publish an article where they use, in a physical system, the so-called Shor algorithm, but they managed to compute 15, okay, to find the prime numbers, prime factors of 15, 3, and 5. So not very impressive. And up to 2019, everything that was done experimentally, not on paper, not theoretically, but experimentally, everything that was done so far, pretty much everything, was not what we call a quantum of any quantum advantage. So what you call a quantum advantage, what a lot of media call quantum supremacy, perhaps not the best term, but the idea is the same, is what actually so far, what is there? Is there an experiment? Is there something? Is there a system that has been shown that quantum physics can actually beat any classical computer on Earth at this time? Okay? So up to 2019, it was not the case. So everything that was done in labs, in laboratories, we could do with even perhaps with your phone. You didn't even need perhaps a supercalculator for that. But in 2019, so this quantum supremacy, so-called quantum supremacy or quantum advantage, there are some discussions, but pretty much it was realized by the sort of Google team using superconducting processor, so using superconducting qubits, which we haven't talked about yet much, but whatever, some physical system in a very cold fridge, where they could make quantum gates using quantum bits, using quantum entanglement, all these notions I talked about, and actually use this to realize something for the first time that was done in a very sort of quick time using their quantum computer, for physical quantum computer. You see a picture of here. This is the chip where you have all these superconducting qubits on them. For the first time, they showed here, in this article, in this work, that what they realized with their computer was more powerful than any classical supercalculator that exists on Earth at the time. Okay? that for the first time, this very first demonstration was sort of impossible to do by a classical computer. So for the first time, so that was in 2019. Again, there are some discussions whether, but let's say this is about the time that we can see the first time quantum advantage, meaning that there is a reason for carry on into that, because quantum advantages for different problems, like I talked about optimization problems or solving the energy levels of molecules and so on, those problems, could be solved by quantum advantage. And that's what we are at, and that's what we want to achieve. Okay. So what about the market? Okay, so for the UTT students, I'm talking to students who are going to become engineers. So one thing you want to do is to have a job. And perhaps you want to have a job in quantum technologies. But are there any? Well, the answer is yes, there are any, and there will be more. I already mentioned that there are some national government, and so all of this is more sort of national national plans, national policies by governments to promote quantum technologies. But as you will see, there are also companies, a lot of companies, working into that field. So here are some predictions of how the market will grow from 2020 to 25 to 2030 in quantum computing, quantum sensing, and quantum communications. And we are talking about, billion dollars coming up. Actually, we don't know that. Those are predictions, but what is pretty clear is that something is up. If you look here, for instance, this is one thing you can find on the internet, but there are others, and it's not up to date, of some of the startup companies working on quantum computing or quantum computing related problems just within the European Union, either on the hardware or on the software or on both, on some applications. So this is just startups company in the European Union at the time, and is not up to date because it almost changes every day. And you can see what are the applications: security and encryption, chemistry and pharmacology. There are others. There are from operating systems, companies working on software, because we need software to run efficiently these to be quantum simulators and quantum computers. And then some hardware, so computer hardware, but also components and materials. You have a whole lot of companies working on actually making components. I mentioned earlier that for the quantum supremacy here, for using superconducting qubits, you can see here, a huge cryostat. You need to be at a very, very low temperature. And you need a lot of electronics in order to control your superconducting qubits. So there's a lot of engineering into that, a lot of physics and a lot of engineering. So potentially a lot of work to build cryostats, to build electronics, to build detectors, and so on and so forth. But also, as I said, in software, there are a lot of companies working into quantum software, because if I give you a quantum computer tomorrow, then it's like the story of classical computers. You can run algorithm, but maybe there are some better ones. Maybe there is a better algorithm than Grover's one. Okay? So you need to be able to work on that. And you need to be able to work on the software as well, as in the interface between the physical system and the user. Again, nothing new in classical computation, but you need that for the quantum counterpart. There are also some, so by the way, I highlighted this one because this one will be, as I said, talking about quantum cryptography, this sort of British startup company. There are also big, major companies that have been working on the subject for years, or more recently. IBM, for instance. IBM was one of the pioneers working on that. In fact, Shaw was working for IBM at the time. But you see also Google, we talked about, Alibaba, Airbus, Nokia, Fujitsu, HP, and so on. Atos, the French companies, Atos and Thales, which are going to deliver some lectures, Intel, and so on. And again, this is not up to date. Okay, there are some major big companies that are every day going into that game. Okay. So, to conclude, I can say a few things. So first of all, the message I want to make sure that you get at the end of the 14th lectures is that first of all, quantum technologies have a future for you, and each of us, pretty much, even day-to-day, in our day-to-day life, we will encounter quantum technologies. This is our future. And for that, as you saw, there are many different aspects that we need to understand, to grasp. Not just physical aspects, but also mathematical aspects and computer science aspects. And at the end, so all of this here, so some of these I already talked about, but all of these sort of symbols and names and diagrams and matrices and so on, which for the moment seem a bit unclear and sort of rather esoteric, then the goal is to, at the end, hopefully, that those issues will be clearer for you. So I gave some examples. So for instance, what you see here is, if you look at quantum technologies in terms of, so if you look at publications on, say, a quantum algorithm using photonic qubits, so using photons, then you will see a lot of diagrams like this. Okay? So for the moment, they don't make sense to you, but hopefully some of these will make sense at the end of it, because as I said, I will use photons as a practical case for explaining how we make qubits, how we make quantum gates and algorithm in real life. There are other systems, but this is the one I will use. So by the end, you should kind of have an idea of at least, what it means, what are those weird symbols that we use. We talked about the wave function, psi, which, as I said, for now is something that describes your system, your quantum system. Sorry, something that quantum mechanically describes your system. So hopefully this also, and this why we use this notation will be clearer at a later stage. Why then this quantum system can be in a superposition state. We already talked about this today. But also the notion of block sphere, that whether every time you talk about quantum technologies, there's a notion of block sphere that comes into play. So we will talk about this, why a block sphere is useful. It's useful because the block sphere is actually a nice sort of geometrical representation of your qubit. So this actually is a qubit, a quantum bit, this particular wave function. And the block sphere is a nice way of sort of geometrically representing it. And we will describe that in more details. Then some sort of, again, esoteric mass behavior, like the so-called tensor product. So how it works, okay, if I use the tensor product between these two wave functions, which actually can write like vectors, so we will see that soon, that in fact a wave function like this is a form of a vector. So if I have two wave functions, I can make the product between the two, but it's a particular product that we call a tensor product, which means that you go from the product of two vectors of 2D dimension to one vector of 4 dimensions. Okay, so you increase your mathematical space from 2D to 4D. And that, by the way, is very important in order to understand the power of quantum computation and this parallelism I talked about at some point. Then we will see how and why a C0, a control NOT gate, I talked about earlier, which is a gate that you can do between 2 qubits, why it looks like this, why this C0 gate is actually a 4x4 matrix between 2 qubits, and why it looks like that. And how we can represent this sort of mathematical object into this language, which can be to higher stages, can lead to quantum circuitry. So this is a simple quantum circuit where you have inputs, zeros or ones, and then you have gates, quantum gates, which are or not relate to each other for each of these input qubits, and an end state at the end, which in this case looks like 3 zeros plus 3 ones. So again, at this stage, this is not so clear. But hopefully, step by step, we should be able to understand these quantum circuits, why they look like that, how we can make a C0 gate, or this one is called a Hadamard gate, on a single qubit or on 2 qubits. And then we will see also some very important people. That's more for the quantum communication part. But usually in cryptography, and this was taken from the sort of cryptography community, is when you want to make a communication, you have a communication between 2 people or between 2 points A and B. And usually we give names to these points, so we call them Alice and Bob. Okay, so you will hear about Alice and Bob quite a lot during these lectures. And it will make sense at the end how we can link Alice and Bob using quantum communications, quantum entanglement, and do quantum cryptography, for instance. So this is it for today. So this was, again, sort of an introduction to the whole subject, to, again, why you should care, why is it so different, and why we are here, why we should do this. And next lecture, as I said, will be before we talk about quantum circuits, quantum gates, and so on. We need to have a step back in order to understand what are classical gates and a classical computer. I'm not going to give a course on computer science, but at least gives what is necessary to know where we start from in a classical view. And then the lecture after that, then we'll go into the notion of defining quantum bit, and then 2 quantum bits, and then gates, and then algorithm, quantum error corrections, cryptography applications, sensing, and so on and so forth. And with that, I thank you, and I will see you next week for the next course. Thank you.